Well, hi, this is Ira Gorlick, and this is the lecture on the history of telecommunications, Part 1. Part 2 is going to be the Internet, but I wanted to go over the history in terms of circuit switch because it's important to understand how they coexist and what they are. Let me start with the videotape, as I showed earlier in the previews, in the introduction, about Ted Cruz, when he makes some comments about the history of telecommunications. So I'm going to play that right now, and I'm going to come back on the other side.
What happens when government starts regulating a service as a public utility? It calcifies everything. It freezes it in place. Let's give a simple contrast. The Telecommunications Act of 1934 was adopted to regulate these, to put regulations in place, and what happened? It froze everything in place. This is regulated by Title II. This is not. Your smartphone, the internet, the apps, all of this is outside of Title II. The innovation is happening without having to go to government regulators and say, "Mother, may I?" We want a whole lot more of this and a whole lot less of this.
Okay, so he makes a number of comments. Let's just look historically at what he said. So some technology history. I'm going to go over the switching history. I'm going to talk about manual operator-completed calls, then electromechanical using electric pulses, and then computer-controlled using tones. And this is important, and it's important for this is actually a key piece to this whole class, that telephony is both by reality and by design a scarce resource. And so whenever you have a scarce resource, it requires some additional thinking in terms of how it's to be managed. So let's just look first at the communication networks, particularly in terms of spectrum, switching, and the physical right-of-ways are expensive and a scarce resource. And when we get into telecommunications, the business side, and I talk about the history of business, we're going to talk about it in terms of right-of-way. And we talk about regulation. We're going to talk about the 1888 Post-Roads Act in terms of providing right-of-way. So this is a very important topic. It's why I've put it in red, and we'll go over it in more detail. In addition to the scarce resource as being a physical reality, rights-of-way, spectrum, those kind of things, there's also the notion that telecommunications works in an optimum traffic engineering environment. In other words, you may have a community of 100,000 people, but you don't have 100,000 trunks coming out of that community, telecommunications trunks. You may have some number less than that, maybe 100 or 1,000, whatever it is. And so what you're doing is you're managing to those optimum number of trunks. And this is important, again, in terms of how it's managed, who manages it, and what is the goals of the management. So recognize that the reason we even have this discussion about net neutrality and the role of government is that telephony in both physical and design situations, design criteria, is a scarce resource. And now you may disagree. And in fact, let's talk about it being a scarce resource. There are many people who think that it's not a scarce resource and there's plenty of resources and therefore it doesn't need to be managed. And that's certainly something to be discussed. In terms of traffic engineering, I just want to make one more point that the optimum use of resources balances cost and requirements. In other words, I can have no blocking in my network, but I'd have to spend a lot of money and it's not worth it. So you try to find the optimal amount of cost versus requirements. We have it in our roads too. We can build 10-lane roads wherever we are, but if there's not enough traffic to justify it, it doesn't justify the cost. And this is also important, is that, especially when we talk about net neutrality and the reasons for net neutrality, the whole discussion about video bandwidth, is that the network is designed to work optimally at a certain amount of traffic and uses certain assumptions in terms of length of call, the number of call attempts, so on and so forth. If any of those change, then the engineering has to change. So, in summary then, this scarcity is why the community believes they should be involved. And we can talk again about whether scarcity actually exists or not and how that's nuanced, but I think this is the fundamental piece. So let's look at some key dates in history. 1884, Morse demonstrates the electric telegraph. In 1876, Alexander Graham Bell invents the telephone. And of course, you know, there's a whole discussion about Elijah Gray and whether Bell invented it or Gray invented it and who invented it first, blah, 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 blah. But this is not necessarily a discussion on those nuances. It's just recognize that the phone was invented in the late 70s. And then in 1892, Stroger developed the automatic switching. The electronic pulse switching was critical. And again, when I talk about business, I'm going to bring this more up. This is more the technology side. And another critical factor, critical invention, was the vacuum tube, Lee DeForest. I'm going to talk about that. And then finally, the transistor integrated circuit and lasers in the 40s, 50s, and 60s. So those would be, in my opinion, the five key dates or key periods in history that, from a technology standpoint, had an impact on what we're going to talk about when we talk about net neutrality. So telephones started out unswitched. You had phones were connected to each other. We call that circuit switch. And by the way, circuit switch is going to be important. I'm going to talk about that in a second. But it was unswitched. And then, obviously, you couldn't have one phone connected to every phone, or you couldn't have every phone having on your desk with everybody. So we came up with the manual switch. It's pretty cool. It's an interesting story too. They started out with boys doing manual switching and found out they were too rowdy and ended up going with women. If you want to Google that, it's a great story. But then manual switches, and then Stroger invented the automatic switch, and again, I'll talk about it when I talk about business, but he did it because he thought that the manual operator was directing people away from his business. And then based on the automatic switch, we came up with the telephone exchange and a national network. And you see the way it's laid out here with the customers and then a local exchange and then the long distance. We have the local exchanges and then long distance. And that's the way the network worked, and it worked good. It optimized the amount of cost and optimized traffic. So now you had many customers going into a switch, and then most of the calls would be local, so you wouldn't need a lot of long distance. But then as you added long distance, you can add long distance trunks. Now let me introduce you to the cloud. We in the telephone company started to use the cloud. Let me go back here for a second. You can draw it out with all the boxes like this, or what we ended up doing is just drawing a cloud. There was no reason to draw what was inside the cloud. We knew stuff existed in the cloud, so you ended up having this kind of a diagram. And this is the same as this, only instead of drawing the individual elements within it, you just drew a cloud. And so that's, by the way, where cloud computing came from, is the history. If anybody was curious where the term cloud came from, that's how it came about. Now I want to talk about circuit switch. I'm going to use the same diagram, and this is important. So let's say I wanted to make a call from Los Angeles to Washington, D.C., from 213 to 202. The way that would work is that the local phone, the local phone would dial, 202-555-1212. It would go into the local exchange. The local exchange says, okay, you want to call area code 202 or long distance. I will connect you to the long distance operator. Long distance operator says, okay, you're coming from Los Angeles. Now you need to go to Washington, D.C. So I'll make a connection within the long distance network to Washington, D.C. And then the long distance network then connects you to the local carrier that handles 555. So it'd be 202-555 in the local carrier. And then the local carrier then would connect you to the phone that had 1212. So that's circuit switched. Once that person picked up the phone, there was now a completed circuit, a two-wire circuit between Los Angeles and Washington, D.C., and it was up and it was in place, and it took up resources. That was a dedicated circuit now. And if nobody was talking, so be it. The circuit was still working, and that's circuit switch, and that's the way it worked, and it worked well for a long time. There was no way not to do it that way, so it worked, and everybody was happy. Problem is, of course, that the local loops, the lines were all a scarce resource. So you were using, this was a very ineffective method or a very inefficient way to use a scarce resource. Now I'm going to change gears a bit for a second and talk about the long distance amplifier and Lee DeForest. Here's a picture of one of the ads for Lee DeForest with a picture of his Audion, which is what they called the long distance amplifier. And that made a huge difference because before the amplifier, long distance was very difficult and not very good. So AT&T bought the patent for the Audion in 1913, and the patent gave AT&T a huge technical advantage in long distance quality. AT&T used that technical advantage to gain a virtual monopoly by interconnecting local phone companies that were either completely owned by AT&T or agreed to all of AT&T requirements. So this is an example of where this is outside of the government. This is just AT&T acquired a patent for great technology. They had the technology, so they were able to dominate the market because of that technology. It's a great thing, lasts a long time. So this is important. We'll talk more about this when we talk about the telecommunications business. And then in the 50s, 60s, and 70s, with the invention of the transistor, by the way, by Bell Labs, and then the integrated circuits, we now are able to replace electromechanical switching with computer signaling. And as a result of that, SS7 was born, Signaling System 7. And so I'm going to talk a little about Signaling System 7 because it's important. So what is Signaling System 7? Signaling System 7 is also known as the Advanced Intelligent Network and can be characterized by three unique things. Out-of-band signaling, which we're going to call metacommunication, which I'll describe in a second, packet switching, and then a vendor independence through standard network elements and interfaces. Remember when I talked about AT&T using the Audion patents to demand requirements of everybody, at this point in the late 70s, we were so upset, the industry was so upset with having to be so restricted in who you can buy from, that the idea of having vendor independence through standard network elements made a lot of sense. So what are some of the drivers? I'm going to read it here. The main force motivating the intelligent network was a telephone company attempt at vendor independence, so telephone companies could get better deals from their suppliers. Intelligent network specs were meant to encourage vendors to design their equipment to work in a multi-vendor environment, to interoperate. And this notion of interoperation and interconnection is critical throughout the net neutrality discussion that I want to talk about. But again, I'm going to bring that up more when we talk about the business side of it. However, SS7 also made better use of the scarce circuit switched resources and offered a couple of cool new features that we can't live without today, like caller ID and 800 calling. So what we found is SS7 was designed in a way to get vendor independence, but it also showed better usage of the scarce resource. And I'm going to describe exactly what I mean by that. So before I do, though, I want to just talk about a few of the side benefits for SS7. Routing calls to a different 800 number than the one the caller originally called, call forwarding, and I'm going to show you how that works, was brilliant, and in fact created the environment today where we have these national and international call centers. You call one 800 number, but you don't know where that's going to end up. You gave additional caller choices on how the call was going to be completed. Credit card and third-party calling or operating calling was enhanced. You could verify the calling number in real time. Supplying calling party numbers directly to the consumer. I mean, calling ID, it'd be absurd to even think about not having caller ID today. So this is the diagram of SS7. We talk about SS7 signaling links. We talk about voice circuits, and then the three network elements are the SSP, the service switching point, which would be equivalent to the old exchange. The STP, which is a new network element, is called a signal transfer point. And the SCP, the service control point. So let me go back to how circuit switched worked before. You dialed a number. Let's say I want to call Los Angeles to Washington, D.C. I then called the number, a circuit was put up, and the call was connected. Now, if that phone was busy, if that 202-555-1212 was busy, I wouldn't know that until I actually delivered the call. So I've now tied up all these network resources for a busy signal. And that's just not efficient. So let's look how, because it uses a scarce resource and it's just not efficient. So let's look how SS7 works. We now have this new thing, these SS7 signaling links that I put as a dotted line here called meta-communication. So we start with this architecture. We start with the same call, 213-555-1212, who's calling 202-555-1212. Calls, the number is dialed, and the SSP says, wait a minute, before I do anything, let me see if that number is available. So it sends a number to the STP. It sends your number along with the dialed number to the STP. The STP says, okay, I know where that is. That's at this exchange. It then delivers that to the exchange. The SSP then says to that exchange, okay, I have a call for this. Are you available? If you are, then it works backwards. It says, okay, now I'm going to make up a connection between your phone and me. Then I'm going to make a connection through the long-distance network to the local, to Los Angeles. And then if you're still available, then I'm going to make a connection to you. So you see how that's much more efficient. You see now you're not tying up any network resources. It's still circuit switched, but you're not tying up any network resources until you know you can make the call. So this is inherently more efficient. Now let's talk about the 800 number, which I mentioned was the other important feature. So let's go back and put up my diagram. Now let's say you have the Los Angeles is calling an 800 number. Again, calls the SSP. The SSP says, okay, it's an 800 number, so let me forward to the STP. The STP says, oh, if it's an 800 number, I need to go to this SCP, a service control point, which is essentially a computer. And the computer says, okay, well, that 800 number really is going to be forwarded to 202. So it then goes through the process, notifies 202, and then the call is set up. So that's the beauty of 800 numbers. This is how call forwarding works, by the way. So this gave a lot of capabilities because now this computer can say, okay, depending on the time of day, depending on how busy it is, I can route that call to any number of numbers. And so that's just a brilliant use of network resources. Now, the meta-communication SS7 used this new transport technology called X25 to transport this meta-communication. And by the way, there's a movie called Father of the Bride with Steve Martin. And there's a line in it in the middle, when the son-in-law is telling him what he does. If anybody's seen that movie, knows that he says he works on the .25 network. This was really big during the 80s and 90s. So X25 was an international standard, and it introduces a new concept from circuit switch. Now I get to where we talk about circuit switched from what we call connection-oriented, which is circuit switch, to connectionless, which is a packet network. We call it packet switch versus circuit switch. And packet switching is much more efficient than circuit switching because you're not tying up resources. So let me look a little at the X25 protocol a bit. It's based on a CCITT recommendation, first published in 1976, has multiple revisions, it uses packet networking, and it was designed to be used by telcos. So it is a network to be designed to work well with like an SS7 network. This is a model of the X25 protocol, and this is going to look a lot like, when we talk about the internet, this is going to look a lot like the internet. In essence, this is the foundation architecture for the internet. It uses different terminology we're going to see in terms of in the internet, the DTEs would be endpoints and the DCEs would be routers. They call them multiple nodes, but essentially it's the same internetwork protocol. Now I just want to go quickly over wireless because, again, Ted Cruz talked about wireless. So let me talk a little about the history of wireless. Again, this is just from a technical standpoint, not from a business standpoint. In 1843, Michael Faraday demonstrated that space can conduct electricity. This was just brilliant, and this idea has now become what we take as what we know as wireless. In 1865, I think this is really cool, that a Virginia dentist showed that the Earth's atmosphere can be used to conduct electrical conductor by flying two kites that were rigged with copper screens and wires, and they were 18 miles apart. Very cool. Then in 1921, the police department of Detroit becomes the first to use mobile radios. There was a lot of problems. They encountered a lot of problems like interference and overcrowding. And this again goes back to the whole Ted Cruz, when Ted Cruz talks about no government interference. Well, it was the community that got involved to help fix some of the problems with overcrowding and interference. And so you have to look at the history in terms of what Ted Cruz was saying. Some more of the history of wireless. I've got in 34. The Congress created the FCC to help manage all these radio channels to make sure that they were effective. In 1940s, mobile radios became much better. And then in 45, the first mobile telephone service was established in St. Louis. But again, it suffered from a lot of massive interference. In 47, AT&T comes out with the first radio car phones. You can read here what it's saying. Then in 49, the FCC authorizes the widespread use of these radio waves and created the radio common carrier. And we're going to talk about common carriers. We're going to talk about the whole thing of the commons. We're going to talk about the role of government. And so here's an example of when Ted Cruz says, sort of all these bad things that happen. Well, here are some of the things that happened that were fairly good. 64. They came up with a new system called push-to-talk. Then in 69, self-dialing capabilities came along, and this became known as IMTS, which was the original, when we talked about improved mobile telephone service. And then in 1970s, cell phones started to be thought about, and we started to allocate frequencies. The 800 megahertz, which was the first frequencies that were deployed in the 80s, but this was envisioned in the 1970s. And then in 1971, AT&T proposed what we now know as a cell system. And in 1975, along with Chicago, which became Ameritech, but Chicago Bell, deployed the first cellular network. So now let me go back to Ted Cruz and show you Ted Cruz's a video again, and then I'll come back on the other side.
What happens when government starts regulating a service as a public utility? It calcifies everything. It freezes it in place. Let's give a simple contrast. The Telecommunications Act of 1934 was adopted to regulate these, to put regulations in place, and what happened? It froze everything in place. This is regulated by Title II. This is not. Your smartphone, the internet, the apps, all of this is outside of Title II. The innovation is happening without having to go to government regulators and say, "Mother, may I?" We want a whole lot more of this and a whole lot less of this.
So, in summary to what we've talked about, and in all due respect to Ted Cruz, a lot of innovation happened even though telephone industry was regulated as a utility. If you listen to him, he acts like you had this black phone, and it stayed that way throughout the 30s, the 40s, the 50s, the 60s, the 70s, the 80s, the 90s. And I showed you is that that's just not the case. There was a lot of innovation. And most of the innovation came from AT&T, which Ted Cruz says was a regulated utility. So when we look at transistors, we look at cell phones, all that stuff came out of AT&T, came out of a regulated utility. Now, we could have a good argument whether it could have been faster without it being a regulated utility. But then you could have had the argument that it could have been slower because there might have been more conflict. And that's going to be the thrust of our discussion. But, let me just summarize again. We got automatic switching through as a regulated utility. We got cell phones and cell networks as a regulated utility. We got packet switching. We got the advanced intelligent network. We got international calling, a great network. By the time the 96 Act that Ted Cruz doesn't mention rolled around, where a lot of this changed, we actually had a lot of innovation. So my point is to you that are watching, and this goes back to confirmation bias. It goes back to everything else. Let's not look at one size fits all. Is regulation horrible? No. Is regulation bad? Perhaps. Could regulation be better? Of course. Might no regulation be even better? Absolutely, we can talk about that. But to just hold up a cell phone and then hold up a black phone and say, this is what happens when you have regulation, this is what happens when you don't, you just have to look at history. Now, I could be wrong, and I'd be interested in the discussion whether you think I am wrong and how this might be better. Anything I got wrong, I would love to correct, because I'd rather find out I'm wrong and change than continue to believe I'm wrong. So this is a longer lecture, but hopefully you liked it, and we'll move on now to phase 2 of this history part, where we talk actually about the innovation of the internet. Thank you.